The class coming up is on transfer functions. Transfer functions are very important in engineering, and we're going to be looking at a low-pass filter, a simple RC circuit with one resistor, one capacitor, some input signal coming in, and look at the output signal. And we're going to do it three ways. The first way will be using Green's functions, and that's a very advanced way. It will give us a solution that includes a steady state solution and also a transient solution as the problem begins. Then we'll go to a simpler way of doing it using phasors, which engineering students learn in introductory courses. And the third way, we'll look at it with a Fourier Transform. And when we go to a Fourier Transform space, we'll find a solution. What we're interested in is the transmission, what goes through the filter. Like if you have high frequencies or low frequencies, like what's the percentage or what fraction? So imagine an oscilloscope looking at the input wave, say it's like 10 volts. And then what happens when you go out of the filter? It might be 6 volts. It might be close to 10 volts. If it's a low frequencies pass, it'll be close to 10 volts. If it's a high frequency, it'll be close to 0. And the higher the frequency, the less percentage will sneak through the filter. I hope you enjoy the class. It has lots of engineering applications.
Class V. Class V. Transfer functions. The first thing we're going to do is look at driven oscillations on, or let's say and an LP, which is low pass filter. Now, a low pass filter passes low frequencies. Here is a very simple one where you have one resistor and one capacitor. And we are coming in this way from the left, as if reading here this way. And this is going to be the out that way. And an observer here with a probe, perhaps a voltmeter or some kind of electronic device, oscilloscope, for example. Oscilloscope would be better because this is going to be an oscillation. You're going to be able to see the output. So here, let's put in a simple pulse. What will happen is you'll get some charge up, some charging, and then when the pulse drops to 0, there'll be a discharge. So here, during this short period in here, the capacitor will start to charge up. It may not charge up fully, depends on how long this is, but when the pulse drops down to 0, then there'll be a discharge. You'll have the exponential decay. So this phase here is charging, and this is discharging. And eventually I'm going to be replacing this with a sine wave, a sinusoidal situation, so that on the oscilloscope one could see the output. So this is a low pass filter, which we will explain why mathematically, but you can think of it that it takes time to charge up that capacitor. If this is a long period of time where the pulse is high, the capacitor will fully charge up and then discharge. You can imagine fully charging up, discharging, fully charging up. So you'll see that on this end. But if you're going very rapidly, like this, then the capacitor won't get a chance to charge up. So you send in charge, but then you, like pulling it back, you're going here with an oscillation. That's not giving the capacitor a chance to charge up. So this high pass, this high frequency wave will not get through. You won't be seeing that. It'll be attenuated. But we're going to show this all mathematically. So if we consider this the voltage V of t, then the voltage V of t is equal by the Kirchhoff's loop rule. Like if you went around this loop, you'd have to get 0. But if we look at from point below here to the top as being V of t, that's going to be the same as the leg that has the R and the C. So that would be equal to the voltage across the resistor plus the voltage across the capacitor. Now this voltage is given by Ohm's law, IR, and the voltage across the capacitor is given by the charge Q over the capacitance. And I is the current. Later in this class, we'll be defining the square root of -1 to be J, because I is sacred for current in engineering. Notice, though, that here I is going to be the derivative of the charge with respect to time. This is the current. And if we look at this equation here, V of t is equal to IR plus Q over C. We're going to write this now as a differential equation where the I is going to be dQ dt. So VR is, V of t is R times dQ dt plus Q over C. And we will divide by R, have the voltage divided by R to be equal to dQ dt plus Q over RC. Now, if we recall, when we dealt with our radioactive dumping problem, we had the change in the number of particles equal to minus some constant times how many particles were left plus the dumping function. Now, if we look at that dumping function over here, one side of the equation, we get then dN dt plus lambda n. This looks like the same equation. Here you have the lambda is equal to 1 over RC, and the n is being replaced by the charge. And the F, this is your F here. This is your F of t. So we already know what's going to happen in this case. We have a convolution problem. So what we'll do is recall from this problem that the convolution dealt with a Green's function that was simply e to the minus lambda t. So by making the association that lambda is 1 over RC, then this Green's function here, the non-shifted Green's function, is e to the minus lambda t, just like we had before. And that means the solution, the general solution for arbitrary functions, f of t, the solution being the charge on the capacitor, which is also related to the voltage that you see across the capacitor. So this is what you're looking at with the oscilloscope. You're looking at the V sub C. So if we have the Q as a function of time, we will then have the V, the voltage, output voltage, as a function of time. All right, so if we then write this as the convolution, this is going to be from 0 to t, and this is going to be then here f of u, e to the minus, and here we have the shifted Green's function, t minus u, just like we did for the radioactive decay and the dumping function and the decay. Here the dumping is putting charge on that capacitor by analogous treatment to the dumping of the radioactive waste. So this here is the Green's function, the shifted Green's function, the general form. Here is e to the minus lambda t minus u. Use a time variable that we're going to integrate from the past up to the present time. So that's our solution. And here, the q of t would be then from 0 to t, and our f is going to be, let's say we're going to pick one. Let's pick for our problem f of t to be some constant voltage amplitude undergoing here a sinusoidal oscillation. That's a sine wave, a simple sine wave going into the system. So this would be then v sub 0 over r, and this would be a sine of omega u, because that we're going to integrate over that time variable, e to the minus, say, lambda t minus u du. So let's work this out. Now, the integral with the sine is a little scary, but integrals with exponentials are not. So if we were to write here, this, we're going to use the Euler relation, where you have e to the I, theta is cosine theta plus I sine theta. And then what we'll do is we'll take the imaginary part of the answer. So let's bring the r over here, because I don't want to keep writing that r out a lot over there. I like to simplify things over here. R, and we'll divide by v naught over here, so things look simpler on the right side. So from 0 to t, we have here then just the sine and omega u, and I'm going to substitute in Euler just a second, e to the minus lambda t minus u du. And now it's time for Euler. So when we do Euler, we'll have to look at the imaginary part. We'll want the imaginary part, which is going to be the sine part. The imaginary part, we're going to go from 0 to t, and then we have e to the I omega u. So here's where the sine is being promoted to the exponential, but we're going to take the imaginary part, since the imaginary part has the sign, and that's what's going to help us work this out easier. And then this is e to the minus lambda t minus u du. All right? So let's note that we can take e to the minus lambda t out, since there's no u there. So if we have here r qt over v naught is the imaginary part. In fact, we could put that, we can make room and put this exponential e to the minus lambda t, outside everything, and make the integral look a little bit easier. And this is then e to the I omega u, e to the plus lambda u. And now that looks much easier. So we come down here. This is going to give us complete knowledge of what's going on. So this is e to the minus lambda t. And then we have the imaginary part of the integral. This is going to be a lambda plus an I omega that multiplies that u du. All right. So this is going to be e to the minus lambda t, and this is going to be the imaginary part of, now this integral is easy to do, e to the lambda plus I omega u over lambda plus I omega, evaluate from 0 to t. So if you were to differentiate this, you would pull down the lambda plus I omega, which would cancel down there, and you would get the proper integrand. So that looks good. And now we're ready to put in the limits. So let's let's do that next. So that's R, Q, this function of t over V naught is e to the minus lambda t. And we have the imaginary part of, we have e to the lambda plus I omega, use evaluated t, and then when you put in 0, you'll get a 1. Now all this is divided by the lambda plus I omega. So that's what we're looking at. The first thing we're going to do is multiply top and bottom by lambda minus I omega so that we can get that imaginary number out of that denominator. So that's the complex conjugate of the lambda plus I omega. So if we do that, then we're going to get here, let's go ahead and write out, we're going to have, this is going to be equal to e to the minus lambda t, and then we're going to have the imaginary part. Now we got here a couple things to look at. Why don't we first look at that denominator? That's going to be lambda squared plus omega squared. And then upstairs, what we're going to have is we're going to have here, first of all, this whole thing up here is going to be multiplying the lambda. How about if I write this top one out? I'd rather just write this out as e to the lambda and e to the I omega t. I like to separate that out. So if I separate that out, then I'll have here e, that's a t, e to the lambda t, all right, times e to the I omega t, like that. And that's going to then be minus 1. And then that's going to multiply the lambda minus I omega. So that looks good. And then we're going to work out each part. Now notice that in this first part, when this comes in here, and this minus lambda t hits that plus lambda t, that's going to be 1. So that's a nice simplification that we're going to get. So here, let's write out again. Big R resistor times resistance times Q of T over V sub naught equals. And the first, I'm going to go ahead and put this imaginary one here, but when that comes in there, this first term is going to have just e to the I omega t. And then I'm going to have, I'm going to write this out 2 terms. It'll be this one simplified times this. All right, that's the first thing we're doing, like that. And that's divided by lambda squared plus omega squared. And then I got to subtract now the other one. So the other one here does have the e to the minus lambda t surviving. So since it's real, we'll put it on the left there. And then we have the imaginary part of the lambda minus I omega over lambda squared plus omega squared. Now this last one is easy to do because the imaginary part is just whatever is hitting that I. So this part here is going to be minus omega over lambda squared plus omega squared. That's what we have for that one. This one here, more complicated. So here, the secret would be here is to write this one out, write this out back now with the Euler relation, cosine omega t plus I sine of omega t, right? That takes care of this. And that's going to be multiplied lambda minus I omega. All right. And in the denominator, you're going to have the 1 over, or we'll just write this side. The denominator is going to be this lambda squared plus omega squared. And this one here, we're going to have to deal with the cosine part and the sine. Now here, if you want the imaginary that goes with the cosine part, that's going to be involving this I over here. Let's do the sine one first. All right, so let's do the sine one first. So the imaginary here would be simply the lambda from the right side times the sine. So the imaginary part and divide it by this. So here you're taking I times that lambda. The imaginary part will be lambda times sine of omega t. When I hits this other one, it'll be real. We don't care about that, so we ignore that. And then with the cosine, that one's going to come in and hit this I. So the imaginary part will be negative omega times the cosine of omega t. And that's all. We're finished because the cosine with the lambda is real. We don't want that. So this is what we have here. And of course, we still have the lambda squared plus the omega squared in the denominator. All right, now we're going to collect this and write this out neatly in one line. So the resistor, the resistance, resistor value times the Q of t over the voltage sub naught is going to be equal to lambda sine of omega t and then minus omega cosine of omega t, and all that is over lambda squared plus omega squared. Now, what about the next term? Well, that's coming down here. So if we come down here, we see this minus sign will hit that minus sign and cancel. So this is going to be a plus. The e to the minus lambda t is surviving. And then we're going to have the omega, here omega, and then we're going to divide by lambda squared plus omega squared. So that is it. This gives complete knowledge as to what's going on. And what's very fascinating about this is that this part dies away. In fact, this part is the transient part of the solution. It's the nice thing about the Green's function. We got total information here. We got everything. So we have here, something's going to happen in the circuit that's going to die down to zero. So here, as time goes on here, like as time goes on to, say, to infinity, then this transient piece will vanish. This will go away. And you'll just have the steady state. This one here is the steady state solution. The steady state solution. Now we might want to check that when the things start, we didn't have any charge. So if we have Q at t equals to 0, then this would be 0 minus an omega divided by lambda squared plus omega squared. And this other piece would be plus. This 0 would give you, for t would give you 1, and you'd have omega over lambda squared plus omega squared, and that does give 0. That checks out. This is nice to check that we have 0 charge at the beginning of the problem. So let's look a little more carefully at this lambda, which is 1 over RC. So here in the Green's function, it'd be minus t over RC. And you might be familiar with that from introductory physics. Sometimes this called like a time constant or a characteristic time. So tau, this is a characteristic time of the system given by the product of the resistance and the capacitance. They're multiplied together. So that's going to give you time units, like seconds. And the frequency, characteristic frequency that goes with this, remember that the frequency is 1 over time, or it's like 1 over like time gives you frequency. So if you have like a characteristic time of 2 seconds, then that means it takes 2 seconds for something to happen. You'd be doing a half each second. frequency is 1/2. It's a reciprocal. So this would be given by the flip, all right? So that would be 1/RC, which is what we called lambda, but we would prefer to use a frequency notation. So let's make that as a definition of omega C, where C could stand for characteristic, or it could stand for cutoff. Now this filter won't have a sharp cutoff. It's not an ideal filter, but still, when you get past that characteristic frequency, things are going to start to go down. You won't be getting through. This is the high frequencies are going to be suppressed, as we will see the great detail of. All right, so that looks good. I think we're ready now to do some trick with talking about phase. All right, so for this, what I would like to do is look at the transient, not the transient's gone. Look at the steady state. So let's look at steady state part of the solution. All right, so that would be given by, and we will write down what we just had below. We're taking this lambda that we had before down in here, and we're going to make this lambda is going to be now called omega sub C. And then I'll just write this over again for you so that we have it up top as we proceed. All right, so that would be the omega sub C times the sine of omega t, and then we had a minus omega times the cosine of omega t, and all of that over, it was a lambda squared, now it's going to be an omega c squared plus omega squared. So that's what we have. Now when we look at this, and we're doing theoretical physics, something here is insightful going to occur. And the theoretical physicist looking at this, one idea would be that this is looking similar to your sine of two angles. For example, this reminds one of sine of alpha plus beta is equal to, here you would have a cosine of alpha and sine beta, and plus here there would be sine alpha cosine beta. Now remember, way back in earlier course we said we could derive these things by the rotation matrix. If we have cosine alpha, sine alpha, we're doing a rotation, we have this, and if we did two rotations with two different angles, all right, like this, sine beta minus sine beta, cosine beta, then this would be the equivalent of doing a cosine alpha plus beta and a sine, say alpha plus beta here. And then in here, the other stuff, we don't really need that because we're really looking at the sine one over here. And that would come by taking this product of these two, turn them sideways and hit them with this, so cosine alpha times the sine of beta plus the sine of alpha and the cosine beta. And if you wanted the other one, the cosine of alpha plus beta would be cosine alpha, cosine beta, and then turn it sideways when doing matrix multiplication, and that would be, there'd be a minus sign there, minus sine alpha, minus sine beta. Now there is a minus sign there, so that minus sign here, if you have a minus beta, you would have a sign change for the sine of negative beta. So let's go ahead and do that. If we have the sine of alpha minus beta, we would have the cosine of alpha, the sine of minus beta, plus the sine of alpha and a cosine of minus beta. Now this would still be the cosine of beta. And so now with this minus sign coming into play, I'm going to identify these with these angles after I see that minus sign. That minus sign is going to help me. So here, the sine of alpha minus beta is equal to the plus 1 is going to be here. The plus 1 is going to be your, let's go ahead and write this out, cosine of beta times sine of alpha, this first one. And the second one has the minus sign, and that'll be minus cosine alpha sine beta. All right, now when I look at this and come up here, I'm seeing that the alpha suggests that the alpha goes with omega t, all right, that assignment. And then the beta, it looks like cosine of beta is related to omega c. Over on the second one, if the alpha is omega t, I have the cosine here. It looks like this omega is related to, this omega is going to be related to the sine of beta. All right, so this is an insightful step. And when we look at this, cosine and sine, it's visual, always good to be visual. Draw a triangle. And so you're saying here that if we have a beta, that a cosine is related to omega sub c. So you put that down there, a cosine. And if the sine of beta is related to omega, we put that down there. That's what's being suggested. Then here, the hypotenuse would be omega c squared plus omega squared. And now, look, with this similar thing down here, this looks very, 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 very nice. So if we do this, we can see that the cosine of omega, the cosine of beta, rather, the cosine of beta, all right, is equal to omega c over the square root omega c squared plus omega squared, and the sine of beta is omega over the square root omega c squared plus omega squared. All right. Now, if you want to substitute in up here, let's go ahead and look at this. We have r q of t over v naught equals. If you want to substitute in, the first thing we're going to substitute in is, well, let me just go ahead and write this out for you up here so you can have it again. Let's go ahead and rewrite this. This is omega c sine of omega t minus omega cosine omega t over omega c squared plus omega squared. So this omega c would be the square root of omega c squared plus omega squared times the cosine of beta. All right, just using this equation. I want to plug it in. And this one here, this omega, using this equation, is going to be equal to the square root of omega c squared plus omega squared, and that's going to be then the sine of beta. So when we plug these in this equation, we're going to get here, this is going to be here the sine, I'll put the sine first, the sine of omega t first, and then this omega c is going to be cosine beta, and then minus here, this is going to be over on this side, this is going to be your cosine of omega t times your sine of beta. And notice that that square root is going to knock this down to a square root. Omega c squared plus omega squared. And so now using the trig identity, this is here compared to what we had up there. This is the sine of alpha, which is our omega t minus beta. And that's over the square root of omega c squared plus omega squared. All right. Now, that insight could be arrived at experimentally by experimental intuition rather than the theoretical formulas here with the trigonometric functions. You could reason that if you're coming in here with some sine wave. So this may be some sine wave coming in here, that eventually you're going to drive this thing to be going at a frequency that you're coming in at. However, you expect a phase change. You expect that the voltage across the capacitor be out of phase. So with that insight, you would immediately look for a function of this form, immediately, from experimental intuition. And then stare at this thing, and then remember your trig identities and go that route. So this step, which is like pulling out something out of a hat, is really inspired by, theoretical inspiration that this looks like a trigonometric identity in some kind of form. And then the other is experimental intuition, where you expect to have a single sine function with phase shift. All right. So there are the two ways to do that. And the theoretical physicist is working with the mind and mathematics and equations and thinking. So they would be all like worked out in his head, like a Gedanken experiment, as Einstein would be doing with his work. So that gives us a nice tidy formula. The tidy formula is the Q of t, if we bring the V naught and the R over to the right-hand side, is then sine of omega t minus beta over the square root omega c squared plus omega squared. And the voltage across the capacitor is Q of t over the capacitance, C. So that's the same trigonometric function in phase. So we can write down this final version. The voltage across the capacitor is V naught over RC times the sine of omega t minus beta over the square root omega c squared plus omega squared. That's it. I kind of like to write the omega squared first, but remember that this 1 over RC, that was our lambda that we had defined earlier, and we agree to call that's your omega sub c. So therefore, final result here would be this is equal to V naught omega sub c sine omega t minus beta. And I'm going to now divide by switching the order. I just like to have that variable first and the constant second. And here, if we go back to this little triangle where we had before our omega and our omega c, the tangent of beta is equal to omega over omega c. So that gives us our phase. And if we were to do a little plot, say, of the incoming function, which is a sine wave, something like this, right? Something like that, right? Then what about this with the minus sign? Well, we know that if, say, this is like this is the angle, like the function here. This is, let's just say we're looking at omega t here, right? We're like plotting the omega t, and if you have the minus b, that means you're going to shift this thing to the right. We have looked at that before, where, see, that would be beta. Remember that if you have a function here, f of x, then f of x minus some d, some distance, is going to move this thing down here, a distance d. We've seen that trick before. So that's going to shift things to the right. But if you look at this time where you're at the peak, and this time where you're at the peak, this time along the axis is actually an early time. And this time here is a later time. So what that means is that
your voltage across the capacitor is lagging, that we got here first if we're the input, and then later you got there finally at that top, see? So we build up that voltage there, input early, and then you got it later. So since that is a lag, engineers like to have the angle to be a negative. So what the engineers will do is that often they'll just say, write this out as V naught omega C sine of omega t plus some phase angle, which in this case is going to be negative, which will mean a lag. So that'd be then omega squared plus omega c squared. So in other words, the tangent of this one is the tangent of the minus beta. In other words, just simply let beta be negative phi to get that to occur. So in that case, this would be minus omega over omega c. So there are your conventions that you may find. But what we're really interested in here, for the grand ending, is define what the transmission is, the amplitudes on the oscilloscope. If you take the out and compare it to the in, so if the in is like 10 volts amplitude, then what about the output? So that means we need the magnitude. We need the magnitude, and here the output is going to be our solution. Which is this expression. And we have to divide that by the input, which is the V naught sine. Now, since this is the magnitude, when you have a sine or a cosine, you put down 1. You want the maximum, you put down 1. So really, this is going to simplify. You're going to get here for the transmission, you're going to get the omega c, the V naughts are canceling, and you can then divide by omega squared plus omega c squared. So that's it. That's what's coming out. So now here you can see the beauty of the math telling us that this is a low-pass filter. In the limit, as the omega, this is the driving force, that's the voltage coming in. So you're coming in with a low frequency, all right, so this goes to 0. Then if you look at this, the omega squared will go to 0, and you're going to be left with omega c over omega c. Now it's a 1. That means we're through. We got through, like we're in. Passes through. It's low pass. Low passes. And then if you look at the limit, as omega goes to infinity of this same expression, now there's no omegas in the numerator, just a denominator, so that's going to go to 0. So that means you don't get through. So if you're high frequency, you don't get through. If you're low frequency, you get through. So that's why we call it a low pass filter. So let's look at this transmission again, V out over V in, taking the magnitude, and have this function omega sub c, that's a constant, and then omega squared plus omega c squared. Now it helps to plot this in a way where your horizontal axis here, let's say if we were to start out at point 0, 0, 1, if we make one step, it's then 0.01, and make another step, 0.1, make another step, 1. At each step, you're multiplying by 10. So it's a nonlinear graph. In fact, you can think like a logarithmic. In other words, this is 10 to the 0th power. So if you wanted like the log, the base 10 log, this is a -3, a -2, a -1, a 0, a 1. The log of 10 is 1, 1 0 after the 1, 2 zeros after the 1, 3 zeros after the 1. And that helps us look at more frequencies, really low frequencies and really high frequencies. And say this is 1 up here, transmission is like everything gets through. And say this is like half. So on the oscilloscope, if you have the 10 volts coming in, you'll see 10 volts because it's 1. It's like 100% goes through.
And this 1, when omega equals 1 here, so see, this is your omega. Really, this is omega over omega sub c. Because when omega equals 1 here, or omega equals, if you think of omega over omega c equal 1, when omega equals omega c, that's going to be our case here, where we're looking at the 1 would be this one here. So this is like in the middle here. That's our characteristic. And if you plot this, you get something like hanging high, and then you start to come down here, come on down here, and then you start to, head off to 0. So the graph looks something like this, which is kind of fun to do on a spreadsheet. Okay, you get this. So this is sometimes called the cutoff frequency, where omega equals omega c right there. And you can see it's not an ideal filter. An ideal filter would be everything passes up to the cutoff, then boom, then nothing goes through. So in other words, you have all or nothing. This would be an ideal low pass filter. All right. And engineers can make filters that are more like this. We just had one resistor and one capacitor. If you have like a couple of two RCs in there and more complicated circuitry, you can get filters that are more dramatically decreasing. Okay, so let's go on to talk about the cleverness of engineers, because engineers teach a lot of these concepts to freshmen using phasers. They have figured out ways of doing this. They don't need complete information that the Green's function gives. They don't care about the transient. They just want this transmission thing, and I can show you a very fast way of getting this, which is nice to do, so we can do things in more than one way. All right? So let's look at what happens if you have a sine wave for the voltage, and this V of t that's doing some sine wave. There's a sine wave. And you have a resistor here. And say you're looking at this electrically, you're looking at this, then you're going to look at and see V is IR. All right. Now, if this V is V naught, and we're going to use cosine of omega t, so that we start off, if you look at the horizontal axis and call that 0, when the cosine is 1 here, you have then t equals 0. So we're gonna use cosine to drive this. And that cosine is going to be equal to the current. I'm going to use lowercase I, function of t times r. All right. And here, we're going to look at a solution for the current, I as a function of t. I as a function of t is V naught cosine omega t divided by r. Notice that the current through the resistor here is in phase, and we have a nice, very simple relationship. When we go to the capacitor, things will be a little bit trickier. So here we're going to put a capacitor here. So here's the voltage, and here's a capacitor, and look at what happens here electrically. So here the voltage is going to be QT over C, and it's the charge that's going to be in sync with the voltage source. The voltage source is V naught cosine omega t. So the charge is in sync, but the current, it'll be different. So to get the current, we have to take a derivative. So the current would be the derivative of Q with respect to T. So if we look at the Q first and move that C over to the right-hand side, we have this for the current, and then we take the derivative. We're going to get here a minus omega is going to come popping out, and the C will still be there, and the V naught will be there, and you'll have a sign. So you see now we have a more complicated situation. Here the current had a cosine function, And the V naught here is the V naught cosine omega t, you got the cosine both places. So current is in sync. Here, the current is not in sync. The charge is in sync, but we want to look at the current. So let's look at our tricks with the complex plane. If we recall with the complex plane, all right, we have something like this. And let's say this is going to be your real axis. This is your imaginary axis. And let's look here at something that has a theta, which is your omega t. And so here, that's why I picked cosine, because when t is 0, it's flat there, and then you whip around as the voltage is changing. And this z, as we promote here to this complex plane, z is going to be a phasor. It's a phasor, all right? So that phasor has a cosine of omega t here. You know, if you let this, equal your I theta, I theta, so that's 1 unit, then this is your cosine there. And if I'm looking for something that's going to be a negative sign. So here, if we do this 90 degrees like this, right, then up here, if we look at this thing rotated, this here, this is your angle. This is going to be a minus sine of theta. This is your cosine of theta. So this is your minus sine of omega t. So that's what we have here. So this is telling us that the current here is rotated by 90 degrees. Well, we know it's rotated by 90 degrees because of the trigonometric functions come out right. But we also know that you can get that by doing the trick. If z goes to iz, that also does the rotation trick. Now we can't use I because, you see, we got to make these j's in honor of the engineers, all right? Because I is being used for the current, and current is sacred. So here what we're saying is that if you look at the voltage that's coming in, the voltage that's driving the system, this is the input voltage. If I let this be represented by V naught E to the J omega t, so now here we have a voltage constant in front, a value that doesn't have to be 1 volt, could be anything, and that's a phasor. And I'd be interested here in the real part as for the physics, all right, of what's going on. But this is very, very powerful. Then if you look at the voltage here, say across the capacitor, all right, the voltage across the capacitor, and we look at this and we say that the voltage across the capacitor, it'd be nice to have a generalized Ohm's law where you have the current and you have some kind of resistor, which we'll call the impedance for the capacitance, a generalized form of Ohm's law, impedance. What might that impedance be? Well, you have it. You have it up here. But with the phasor, you're actually multiplying by the J to get it, to get it just right. In other words, the current here, if you multiply things by the J, omega C, times your voltage, original voltage, if you hit this with J, you are going 90 degrees and you're leading. So in other words, the current here leads the voltage for the capacitor. And that makes sense because if you have this capacitor here, what's happening when you send the current and the charge is that, you don't have any charge yet, but you got the current. You got that current going in there. So that current's going in there initially, all right? But then the voltage across here is dependent on the charge, Q, and that hasn't built up yet. So that's going to lag. That's the voltage going to lag. So the current leads the voltage for the capacitor. And here, if you wanted Ohm's law, remember Ohm's law generalized, you have to have voltage there, and then you want to have some current, and then some resistor thing. So here, if this is your current,
then the current is the voltage over Z. So that means that the impedance, the generalized impedance or generalized resistance thing here is 1 over J omega C. All right. And this is what's taught to like freshmen, or just folks that just do an introductory engineering can do this. And now watch the beauty of the calculation here to get the transfer function. That's what we're going to do now. We're going to do here the transfer function the fast way. Transfer function with phasors. All right. So here we have the circuit. There's the resistor. There's capacitor. All right, like this. And the V in is coming in as function of T. There's your R. There's your C. And then you're coming out. You're coming out the other way. Coming out here. And we're looking at what's going to happen. And what we're looking at here on the output, we're basically looking at the output is going to simply be the current times the impedance of the capacitor. And the input, if you look at the input, this voltage is going to be then the sum of these two pieces using Kirchhoff's rule that if I go from here to there, that's equivalent here of looking at the current hitting the resistor and the impedance for the capacitor. So this is I of T, 1 over J omega C. So you memorize that the impedance for resistors are, the impedance for the capacitor is 1 over J omega C. And then there's one for the inductor, the three basic components. But here we just have the resistor and the capacitor. So then if you want to look at the transfer, let's say some H of omega, you want the out over the in. The out, the currents cancel, so we just want this. The in is going to have both. So here's R plus 1 over J omega C. Now let's clean up a little bit. Multiply by J omega C. I get J omega RC plus 1. All right. And then if I want to look at the transmission, I want the magnitude of this. Before we do the magnitude of this thing, let me just get rid of the RC. This is 1 over J omega divided by omega C plus 1. So this is going to be equal to omega C over omega C plus J omega. All right. That looks good. And then here, if we want the magnitude, actually the magnitude can be gotten real easily by just doing this. If you have Z is A plus BI, the magnitude of Z is equal to the square root of A squared plus B squared. But if you have 1 over Z, which is 1 over A plus BI, the magnitude of 1 over Z, believe it or not, is simply doing the same thing down here. Now that looks a little tricky. We probably should demonstrate that, but it's nice to remember this kind of a trick. So to show that specifically, 1 plus BI, you can multiply by the complex conjugate, and you get A minus BI upstairs, and A squared plus B squared downstairs. And now if you want to take the magnitude, all right, the magnitude of this thing, then you want A squared plus B squared square root upstairs. And then here you would square this and take the square root, so that would just simply be this. But then that is what I have up there. So that's a nice trick to remember. And if we do that, we have the result here. And as I like to write the variable first, I'll rewrite that like this. And we have it. You have the transmission function just in a few lines the transmission for the low-pass filter. So when omega is small, you get 1, and or close to 1. And then if omega is large, you get 0 or close to 0. So that's very nice, very nice. One last thing we're going to do today, one last thing, it'll be finished, and that is transfer functions and transforms. Now, Richard Feynman has been known to say that good theorists need to know many ways of getting the same result. So we have gotten the same result by the Green's function, which is overkill if you just want the transmission. That gives you complete information, transient behavior and all. That's a nice tool to have. And then the second one, we use phasors. If we're after the transmission, that's a very nice technique to do it that lends itself to introductory students. And then this is the third way, all right? And this third way is to write the equation down in terms of good old-fashioned physics. So here's your resistor, here's your capacitor, here's R, here's C, and say here's the Vn, function of t. And you see, if you wanted to do the loop rule, Kirchhoff's loop rule, you would say Vn t minus here the current times R, and then minus the voltage across capacitor, instead equals 0. Like that's your loop. Here I just write down Vn of t, that if I went this way, it would be equal to IR plus QC for the other leg, like the two legs are the same. But this is officially like the loop rule of Kirchhoff. You go up here, you gain your voltage, and then you have a voltage drop and another voltage drop, and you're back to ground. And sometimes here the engineers have a little symbol like ground. This is the ground down there. So here is good old-fashioned physics, no phasors. And here we have the input is equal to the derivative of the Q with respect to T, because that's your current, times R plus Q over C. So that's just nice to review. That's introductory physics and the Kirchhoff's loop rule, all right? Okay, so now what we're gonna do, before we do that, let me just write down the output. The output would just be the voltage across capacitors. That's just Q over C. That's all that is, all right? So now we're gonna Fourier transform everything. Now the Fourier transform of Vn equals the Fourier transform of dq dt times R plus the Fourier transform of Q over C, and the Fourier transform of the V out is just going to be the Fourier transform of Q over C. Okay, now the Fourier transform of Vn we'll call capital Vn be some function of omega, because when you take the Fourier transform, you're integrating with e to the I minus I omega. There'll be some function of omega. And this is going to be equal. Now you take the derivative. Remember, derivative of the Fourier transform is square root of minus 1, I, which now we're using j. It's I omega, but now it's j omega, because j is the square root of minus 1. It's j omega, and that's going to be then times the Fourier transform here of the Q, which we'll call capital Q of omega. So the rule is for, when you have the Fourier transform of a derivative, df dt like this, before we had an I omega, we said I omega, and that's then the Fourier transform, but now we're using j, right? So that's what we had before, so that's that one, and this is going to be plus 1 over c, and this is going to be the Fourier transform of the Q. This is very easy here. This is going to be the out Fourier transform, is the Fourier transform of Q over C. Now watch this trick. Take
h of omega as the ratio of the output in transform space over the input in transform space. And then you get q of omega over c. That's this one. And then in the denominator, you have this other one, j omega r times q omega, and then add q omega over c. All the q's disappear. Wow. All the Fourier transforms like gone. Like what was that? All right. And h of omega is then equal to here, with all this gone, you can put a 1 here and put that c in downstairs, j omega rc plus 1. But wait a minute, this is the answer. This is what we got before. This is 1 over j omega over omega c plus 1, which was omega c over omega c plus j omega. And omega c over j omega, got that before. Like we're finished. Like that's it. We got it. This is wild. This is a very elegant method that if you take the differential equation, the standard differential equation in introductory physics classes, all right, using Kirchhoff's law, but now we use the advanced concept of the Fourier transform. In transform space, the transmission coefficient is basically just a few steps of algebra. So another way of getting the same result. So that concludes our lesson on the transfer function. Whenever you have a system that goes from, let's say some energy goes from one form to another, like your ear, for example, you have a sound wave going into your ear, there's a transfer function for the eardrum. It doesn't faithfully reproduce everything. And then the sound has to go through the bones of the middle ear. They will not reproduce precisely everything. So now those functions, they're like a filter or some kind of thing going on there. That's very complicated, but the same principle applies. The transfer function is a very, very important concept in many, many fields. The example I just gave there was in the psychology of perception. We'll see you next time.